Welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today I am going to discuss a very important aspect in the robot dynamic equation, and that is the Newton-Euler equation. Through Newton-Euler equation, we can size the actuators, okay, what actuator has to be picked up, what torque capacity it has to be. So, that we can decide using Newton-Euler equation, in fact using other dynamic equation as well, but in this lecture I am going to focus on the Newton-Euler equation. Okay. So, I hope that by end of this lecture you will be able to understand the recursive nature of Newton-Euler equation and see how can we calculate the joint torque, okay, and size the actuator, the most important aspect in the robotics. Okay. If you are making a robot, what actuator you should use? So, you will be getting answer of that question in this lecture. So, I begin with the introduction of this topic, then we will be seeing the Newton-Euler equation, and we will see that these equations are iterative in nature, okay, and this iteration goes from initially we are going from outward to compute the velocities and acceleration, and we go up to the end effector, okay, from the base frame, and then we come back from end effector to the base frame, okay, and that is what we call as the inward iteration, okay, to compute the forces and torques. Then we will be seeing how do we take care of the gravity forces in this dynamic algorithm. In fact, that concept will be more clear when we will be doing a problem, okay, based on this concept, and that I am going to do in our next lecture. Okay. So, there are various methods to study the dynamics of manipulator, and these methods are say the Lagrangian formulation. This method is energy based, and in this method we calculate the potential and kinetic energy of the robot, and basically then we find out the Lagrangian, and using that Lagrange we get the Lagrange equation, okay, and from that equation we can calculate the torque, joint torque, or the joint force if it is a prismatic joint. If it is a revolute joint, then we can get the joint torque. Okay. So, in the Newton-Euler formulation, okay, this formulation is used to compute the forces and torques required for motion by applying Newton's law for translation and Euler's law for rotation of each link of the robot, okay, and it is very popular for inverse dynamic because it is efficient and it can be implemented recursively. That feature we are going to see over here. The other popular method for the dynamic equation is the bond graph modeling, which is a graphical method for representing energy flow in physical system across multiple energy domains, maybe say electrical, mechanical, hydraulic, electronics, all the energy domain. And this method is very popular in modeling the mechatronic system, okay, where we have the several energy domains participate, okay, in a system. Alright, and this method uses bonds which are nothing but directed half arrows to show how the power exchange between the components takes place, okay, and this way it unified the modeling of the multi-domain system, very popular system. Advantage of this method is that the system equations which you get, they are the first order differential equation, okay. So, it is easy to solve them. You can write it in the matrix form, okay, in the form of a state space equation. Again, this state space equation I am going to take one full lecture on that, so that we will be seeing. So the advantage of bond graph model is that your differential equation are the first order differential equation, and you can write the state space equation from the bond graph model, and then you can implement the control or any other aspect into it, say model reduction if you want to do. All those things you can do. You can check for the controllability aspect of the system. Okay. So, we will consider each link of manipulator as a rigid body, alright. So, the rigid body definition I have already discussed in my last lecture, where we defined the rigid body as a body in which the distance between the 2 points on the body does not change, whatever force you apply on it. Okay. So, if you know the location of the center of mass and the inertia tensor of the link, then the mass distribution is known completely. These things we have seen in the last lecture. Okay. And in order to move the links, we must accelerate and decelerate them naturally. Okay. So, when it is going to start from 0 velocity, we are going to have acceleration, and when say the end effector is going to reach the destination, we are going to have the deceleration, because we want to stop. Alright. So, the forces required for such motion are function of the acceleration desired and the mass distribution of the link. Okay. So, the Newton equation along with its rotational analog, which is the Euler equation, describe how forces, inertia and acceleration relate. That is why this method is called the Newton-Euler method. Okay. So, the Newton equation basically describe the translational dynamics, and the Euler equation describes the rotational dynamics, okay, of the links. So, why do we study the Newton-Euler equation for robotics? Okay. So, it has got great computational efficiency. Okay. So, n complexity order is there. Okay. It is ideal for real time control of multi-degree of freedom robots. Its structure is recursive. I have already discussed, we are going to see in the coming slides how that recursion is there. Okay. So, it naturally handles kinematic chains, propagates forces link by link. It gives the complete dynamics. It captures inertial, Coriolis, centrifugal and gravitational effects. Again, I would like to draw your attention specifically when we do a numerical problem on that. Okay. And you can very clearly identify all these terms. Then the AI integration is very easy with the Newton-Euler equation. It serves as physics prior for learning based and model predictive control. So, let us look at the Newton-Euler equation. So, suppose this is a link of manipulator, okay, and in this one you have a force applied F at say the CG of this link, and this in turn give an acceleration in the link given by the Vc dot, Vc derivative. Okay. So, this force will be m Vc dot, where m is the total mass of the body or the link in this case. Okay. So, that was the Newton equation. Now, let us look at the Euler equation. So, suppose you have a link here say, and in this link has got a angular velocity omega and angular acceleration omega dot basically. Okay. So, naturally these things you will get if you have a moment n being applied on that, and this value of n is given by this I omega dot plus omega cross I omega. Okay. So, if we compare this equation with the Newton equation, we see that this is the additional term which is coming over here. Okay. And that term captures the gyroscopic effect, which is very crucial for spinning robot joint and for the fast manipulation. Okay. So, coming to the iterative Newton-Euler dynamic formulation, computing the torques that corresponds to given trajectory of a manipulator. So, that is our objective here, And with the following information about robot, such as position, velocity and acceleration of the joint, which I describe with the help of these vectors, okay, for the position, for the velocity and for the acceleration. And if I know the kinematics and I know the mass distribution. Mass distribution essentially you see as we have seen, we know about I, that is the inertia matrix. So, if these things are known, it is very easy for me to formulate the Newton-Euler dynamic equation. Okay. So, to begin with, we first perform the outward iteration to compute the velocities and acceleration. So, in this one, what all we do is that we calculate the rotational velocity, we calculate the linear acceleration and we calculate the rotational acceleration about center of mass. Okay. So, this is what we do, okay, and these computation will be done in an iterative way. We can start from the first link and move successively link by link outwards till we reach, say, the last link. Okay. Here a figure shows, say, this is your ith link, okay, and you have the I plus 1th link over here. Now, in this figure you have the ith frame here, which is attached at the beginning of the ith link, and you have I plus 1th frame attached at the beginning of the I plus 1th link. Ni is the moment acting from the previous link to ith link, and similarly Fi is the force acting here from the previous link, and Ni plus 1 is the moment acting on the next link by the ith link. Similarly, Fi plus 1 is the force acting on I plus 1th link by the ith link. Okay. So, this is how these parameters are defined. So, now see the propagation of the rotational velocity. Remember, our aim is to find out the linear and angular acceleration of links. Okay. And to do that, we begin from the first link and we go till the last link, and this is what we call the outward iteration. So, we have already seen this equation, right, propagation of rotational velocity. Okay. So, this was angular velocity of I plus 1th link, okay, expressed in terms of I plus 1th frame is equal to angular velocity of the previous link, okay, of course expressed in terms of I plus 1th frame plus the joint velocity, that is the I plus 1th joint velocity. Okay. So, this is there. So, if I have to find out the angular acceleration, one way is that I can directly take the derivative of this equation. So, this derivative will be this term derivative over here plus this term derivative over here, plus we are going to have one omega cross term over here. Okay. So, this term, okay, cross this term. So, this is what we are going to get the angular acceleration of the link I plus 1th link. Okay. Now, there is another way of doing that. In the previous lecture, where we have seen how the angular velocity propagates, right, we assumed the 3 frames A, B and C, and we said that B has angular velocity with respect to A and C has angular velocity with respect to B, and we got this equation. Okay. Now, in this equation, if I put A frame as, say, I plus 1th frame, B frame as, say, my ith frame, and my C frame is again, say, I plus 1th frame. Okay. So, if I do that substitution, I am going to get this equation, which is going to be nothing but the same equation which I just discussed with you. So, it is this term, right. So, angular acceleration of ith link expressed in terms of I plus 1th frame. So, this is what angular acceleration of ith link expressed in ith frame into this rotation matrix. So, that we get acceleration in terms of I plus 1th frame. So, this term is this one. Then we have this cross term over here. Okay. So, these two terms are same. Again, this is expressed in terms of I plus 1th. So, here I am expressing this omega I in terms of its own frame, and then this rotation matrix cross, of course, this omega I plus 1, and this is expressed in terms of own frame. So, that is nothing but this joint velocity, okay, and this one is basically again the joint acceleration. When your joint is prismatic joint, so naturally your joint velocity is not going to be there, acceleration is not going to be there. So, these two terms are going to be 0. So, this term is just going to be equal to this one. Next, let us look at the linear acceleration propagation. So, the linear acceleration of each link frame origin is obtained by this equation we have already seen when we have seen the velocity propagation, which is velocity of I plus 1th link with respect to some universal link expressed in terms of I plus 1th frame, and this is velocity of ith link again with respect to some universal frame expressed in terms of ith frame, and this is omega cross r term over here. All right. So, here we do the multiplication by rotation matrix from I to I plus 1th frame in order to get these values with respect to in terms of I plus 1th frame. Okay. So, I can directly take the derivative of this equation, okay, one way of doing the acceleration. So, what all I am getting when I am taking a derivative of this one. So, it is this term which I am getting, then I am taking derivative of this one. So, I have this derivative cross this term, and then I will be having one omega cross term, that is omega I cross this omega I cross p I plus 1 I. So, this is what I get. I hope this is fine. Okay. Now, the linear acceleration equation which we have seen previously, that was this equation. And how we got this equation? We assumed a vector here QB in the frame B, and we assumed that the B origin is at a distance P, B origin A, that is represented by that vector, and you have a vector A. So, the acceleration of Q as expressed in terms of frame A is acceleration of this V origin plus omega cross this vector plus omega cross this vector. So, these terms we have seen. Now, if we compare this equation with this one, we can identify these terms by color. So, this is what B origin acceleration corresponds to this one, okay, and this acceleration actually corresponds to this term, and this double cross term corresponds to this one. Okay. So, this one you can just see, if you replace B by ith frame and A by I plus 1th frame, then you will be getting this equation. I leave that as an exercise for you just to see and be confident. Okay. If we have a prismatic joint, then there are some changes going to be in this equation. So, again this is the equation which we have seen earlier in our previous lecture, and so from this equation I get these terms basically, okay, and here I have identified with color, okay, what term corresponds to which one, okay. So, this corresponds to this one, then this velocity of Q in the frame B, it corresponds to this one in case of prismatic joint, okay. Then we have a 2 cross term is there. So, we have a 2 cross term over here, then we have a double cross term over here. So, we get the double cross term over here. So, this way we can get it. So, next what we are interested in finding the linear acceleration of the center of mass of each link. So, here basically my ith frame is here and my I minus 1th frame is here, and my center of mass frame is going to be here, okay. So, you see that if I am expressing velocity in terms of the center of mass frame rather than I plus 1th frame, so the orientation of this center of mass frame is going to be same as that of the ith frame, because both the frames are going to be on the same link, right. So, if I am writing this expression, then my this R is going to be identity matrix. Okay. So, this term will not be there. So, then next you are going to have this term, and this p I plus 1 with respect to I, that is going to be actually this distance in this case, alright. So, this is your p c I basically. So, this we have put in plus your omega I cross here again PCCI plus you have the previous link acceleration. So, this way we can get the acceleration of the translational acceleration of the CG of the link. So, now I have found out the translational acceleration of the CG of link, I have calculated the angular velocity of the link, and I have calculated the angular acceleration of the link. So, now I can write the Newton-Euler equation. So, this is my Newton equation. Okay. So, I can get the inertial forces acting on the link Fi, and similarly I can get the moment, inertial moment acting on the link Ni. Okay. So, this way I can get, because I know this value, I know omega. Okay. So, of course, provided I know this mass distribution, that is I of the link. Alright. So, through this we complete the outward iteration. So, what we have done in the outward iteration? In the outward iteration we have evaluated the link angular velocity which is used here. Okay. We have evaluated the link angular acceleration which is used here, and we have evaluated the link CG acceleration which is used over here, and through this we have calculated the inertial force and inertial moment acting on the link. Next we perform the inward iteration to compute the forces and torque. Okay. So, this definition I have already given to you, alright. So, in this figure, say this is the moment, this is the force acting from the previous link on the ith link. Okay. Here this is the moment and this is the force acting from current link on the next link, and this is the inertial force and this is the inertial moment. So, I can take the force balance. Okay. So, the net force on this ith link is Fii. If I take this value, that is the force coming on ith link from the previous link as positive. So, this value positive and this value negative, that is the force applied by current link on the next link. And here I am expressing this force in the terms of the same frame. So, I have to use this rotation matrix here, so that I express all the forces in terms of the ith frame. So, this is my force balance. Then I can have the torque balance about this center of mass. Okay. So, if I to find out the torque balance about center of mass, I can find out the net torque acting on this link, right. So, this will be this torque coming from the previous link minus this torque applied by the current link on the next link, plus then I am taking the moment of this with respect to this, and this is that distance, your PCI. Okay. So, this moment, then moment of this force, and this is going to be actually this is going to be of what, from this total which is your P I plus 1 I, okay, with respect to I, from this one we can subtract this one. Okay. So, I will be getting this value, right. So, this is what is done over here. Okay. And then everything is expressed in terms of the ith frame. This equation is what we have seen in the previous slide, and now I write this equation. From this equation I write Fii. Okay. So, I write Fii as this one. Okay. So, then if I substitute here, so this term is as it is, this term I am expressing in terms of its own frame. So, it is here. This Fii I am substituting over here. So, you have this term and this substitution comes over here, minus then this term as it is cross this term is there. Okay. So, now this NII is giving me this one, this term as it is. You see minus PCI cross FII is this one, and one term gets cancelled over here, and that is minus PCI into this force, okay, with this PCI into this force. Okay. If you express this in terms of the same frame. So, that is going to be cancelled over here. So, you are going to left with this one. So, finally, I can write these terms as this one, FII is this one and NII as this one, the simplified way. Now, you see this is the, say I know at the tip of the I plus 1th frame how much force is acting. Okay. So, I know this one, I have already evaluated this term. So, I know this one. Similarly, I know what is the moment acting at the end effector. So, I know this term, I know already this term, I know this term, all the length terms I know. This term I have already evaluated. So, I can calculate this, the moment needed at the joint, okay, and I can pick up the z component of out of it, because you know we have assumed the ds parameters right here. So, in the ds parameter we have assumed that the joint rotation takes place about z axis. Okay. So, naturally the torque by the motor that has to be about z axis. So, I take the transpose of that and multiply it with the unit vector and I pick up the z component. So, this is for the revolute joint, and if it is prismatic joint I can pick up that force. Okay. So, this way I can do that. So, summarize, I perform the outward iteration from 0 to link 5, okay. And so, this is my velocity propagation equation, this is my angular acceleration propagation equation, this is my linear acceleration propagation equation, this is my CG acceleration propagation equation, and once I have that I can calculate the inertial force and I can calculate the inertial moment. So, this is my outward iteration, okay. And next I go for the inward iteration, and that iteration I perform from the last link to first link. Okay. So, in this one I know this one from the previous slide, that is the outward iteration. This is the end effector condition, that also I know. So, I can evaluate this FII. Okay. And once I have that, then I can evaluate this, the joint moment, okay, a joint torque, because I know this, I have already evaluated this one, and this is the term associated with what moment is acting at the end effector. This one I have evaluated, this is again the forces acting at the end effector. So, I get this joint torque term, and out of this one I calculate the z component part, okay. And so, that will be my the joint torque or the joint force in case of the prismatic joint. Okay. So, if in this equation if I have to include the gravity also, okay, the gravity. So, how do we do that? So, to do that we can assume the base, that is 0th frame, to have an acceleration g, okay, and that will give a magnitude of the gravity vector, but it points in the opposite direction. Okay. This is equivalent to saying that the base of the robot is accelerating upward with 1g acceleration, okay. And this fictitious upward acceleration causes exactly the same effect on the link as the gravity would, and this we are going to see when we are doing the numerical problem, okay. So, with no extra computational expenses the gravity effect is calculated, okay. Next, let us see how does the AI uses this Newton-Euler dynamic equation. Okay. So, in case of physics informed neural network, okay, The Newton-Euler structure embedded as physics prior to neural network architecture, it reduces the data needed by say 10 to 100 times. Okay. We can have the model based reinforcement learning. So, Newton-Euler dynamic model used for planning in MPC or Diana style reinforcement learning. Agent learns residual errors, not the full dynamics. We can use this for the parameter identification, okay, with linear parameterization. Okay, this can be done. We can have the safe human robot interaction, that is Newton-Euler based impedance control. We can do that. We can tune these parameter KSBS online. We can have the simulation to real transfer. Okay. So, the Newton-Euler simulator provides accurate dynamics to for training, okay, and domain randomization over mass or inertia parameter, that is possible, and we can have the learned inverse dynamics, okay, that is the deep neural network maps these, that is the joint position, velocity and acceleration vector directly to the torque. Okay. So, trained on the Newton-Euler data, okay, and this is used for the real time feed forward without the use of symbolic model. There are various software tools and libraries which are available. I am not going through all of them, but I have kept this slide for those of you who are interested in learning this. Okay. So, the Peter Cork robotics toolbox, either you can do in the MATLAB or Python, it has got full Newton-Euler implementation is there. Then ROS2, which the topic which I have introduced in the first week of lecture, and move it. The KDL library implements this recursive Newton-Euler for the real robot. Then we have the PyBullet or Muzuko. There also this Newton-Euler is used internally. Then we have Pinocchio, where state of the art rigid body dynamics library is there. Drake has got the multi body dynamics. Then Jack's robots has got differentiable Newton-Euler for gradient based optimization and meta learning. So, that is there. So, to summarize, the Newton-Euler equation describe the complete rigid body dynamics. These two equations, dual equations, they describe the complete rigid body dynamics. They are recursive algorithm we have seen. First we move outward and then we move inward. The equation can be written in the matrix form, okay, and this help us in getting structured controller design and analysis. There is very good synergy with AI. Okay. This Newton-Euler provides physics structure, AI learns residuals, unknown parameters or speedups, okay, and it has got vast application in inverse dynamics, model predictive control, gravity compensation, parameter identification, simulation to the real, and for the safe human robot interaction. So, with this I would like to close. So, these are the references which you can refer further, and thank you.